Okay, so we're talking about random variables that have several components. For instance, you could think of the case where you throw 2 dice and each dice takes a different value. So that's going to be a 2-dimensional random variable. Or you could throw 100 dice and you'd have a 100-dimensional random variable. Similarly, you can have an n-dimensional continuous random variable. Suppose you spin a spinner twice, or you throw a dart twice, or you make 2 measurements and you have random error in your measurement. Those would all be cases of 2-dimensional continuous random variables. Okay. Now consider the question. Suppose you have 2 dice in your experiment, you throw 2 dice, but you're only interested in the value of the first dice. Or if you had 2 random measurements and you're only interested in the first random measurement, how do you recover the first random measurement if you know the PDF for the joint PDF for the pair of random measurements? Well, since x2 doesn't matter, you should just sum over all the values of x2 that correspond to the particular value of x1. And that's exactly what we do. And that's what's called the marginal PDF. So let me show this out in 2 dimensions again. Sorry. All right. So let's talk about marginal PDF. Okay. So suppose I have a 2-dimensional random variable, and this is x1 and x2. Okay, and suppose now remember, the PDF is going to be some kind of surface, which I can't draw. I could draw a contour plot, but I think that might be pretty ugly. But I should imagine a surface that's a function of these 2 coordinates. Now suppose I want the probability of that x1 is between A and B. Suppose I want that probability, and that's the probability for this random variable x. I'm not interested in x2, I only want x1. Well, remember, to find probabilities, you have to integrate over an area. So I want x1 from A to B, and x2 can be anything, right? So in fact, I want to integrate over this strip. Okay, so that's what I'm going to integrate over. Now, in terms of this function f, what's the value of that integral? Well, x1 goes from A to B, and x2 goes from -infinity to infinity. Okay, so that's equal to the integral from, I'll put the A to B integral outside, and then here is an integral from -infinity to infinity of my PDF for 2 random variables. And I'm running out of room here, but that's dx1 and dx2. Okay. All right. Now notice what I have here. I've integrated from A to B. Let me write it again down here so we can see it more clearly. Integral from A to B, integral from -infinity to infinity. And what we have here is fx, x1, x2, dx1, dx2. I'm going to write the dx2 on the inside because that's on the inside. Okay. Now, what are we integrating here? We're integrating from A to B this function. Now, remember, when we found probabilities in 1 dimension, how did you find them? Well, we can go up here. I have my handy dandy thing. We integrated the 1-dimensional probability density function to find the probability that a random variable was between A and B. Okay, we integrated the 1-dimensional probability density function. What are we doing here? To find the probability that the first component of my vector random variable is between A and B, I'm integrating this function. So what does that mean? That means that this here is the probability density function of the first component of my random variable. Okay. Sorry, I went a little too far. That dx, this should not, the dx1 shouldn't be included, so I'm going to move that over a little bit. This part here, this integral here, is the PDF of x1. Okay, so in other words, to find the PDF of my variable x1, I integrate it over the other random variables that I'm not interested in. See, that's exactly what he has in this case here. When he wants to find the PDF for a single random variable, he integrates his probability density function over all the other variables that he's not interested in. And what does he integrate from? From minus infinity to infinity. Again, this looks a little complicated, but please just remember the two-dimensional case and you'll be okay. Now, let's consider also the CDF, the cumulative distribution function. So let's remind ourselves what this was like in one dimension and see how we can go up from there. So we'll do the CDF in one dimension. Now remember what the CDF in one dimension was. If I have my x here, and I have my PDF, which may look like that. Okay, if I want, the CDF would be a function of x. So my CDF, the notation that you usually use is capital F, and that's simply the integral from minus infinity to x of the PDF. And now here I used x there, so I'll have to use a different variable, let's say y. Okay, so this is the CDF for, so this is CDF for a one-dimensional random variable. Okay. All right, now let's consider what would the CDF be for a two-dimensional random variable be? Okay, now we have the plane. Okay, now we don't have, if we have a point here, how can we say integrating up to this point? Now this point is going to be, well, represented as x1, x2. All right, now here we integrated, where'd we go? Here we integrated in one dimension up to a point. One dimension we integrated up to a point, and the CDF was actually this area here. Now, how do we integrate up to a point in two dimensions? Well, we should include all of the x1 values smaller, and we should include all the x2 values smaller. So the CDF in two dimensions is going to correspond to the probability of this area here. Okay, so in this case, my CDF, and I write that as f, it's also going to be f of x1, x2. It's going to be a function of my random variable. And the definition is going to be the probability that my x1 random variable is less than or equal to little x1, and big X2 is less than or equal to little x2. Now remember what this means. This means that in my experimental outcome, the outcome for the first component is less than or equal to this fixed value x1, and the outcome for the second component is less than or equal to this fixed value x2. Now, how would we write this in terms of integrals? In the one-dimensional case, we were able to write the CDF as an integral of the probability mass function, or probability density function, sorry. How can we do that in two dimensions? So we'll have an integral expression. Now, remember that to find the probability of an area, we simply need to integrate the probability density function over that area. So that's what we're going to do. We're going to integrate over that area, and we have to integrate the probability density function. Remember the probability density function, we use little f to denote that. So here we'll have I'm sorry, that's not a vector, that's x1 and x2. Okay. I mean dx1, dx2. Now what are the integral limits here? Sorry, that should be dx2. What are the integral limits? Well, x1 is going from, I'm sorry, and I can't use x1, x2 because this point here is x1, x2. So let me use y1, y2. Go back and do that. Okay. Okay, and this is dy1, dy2. Okay. Again, we'll ask the question, what are the integral limits? Well, the integral limits on the horizontal direction are from minus infinity to x1. Okay, doesn't really matter which direction you do this in. Actually, I should make the inner one be agree, so I'll make this be, I can actually make this x2 and this one be x1. Okay, you're integrating in the horizontal direction from minus infinity to x1, and you're integrating in the vertical direction from minus infinity to x2. And you're finding this area here, which is kind of the lower quadrant corresponding to this particular value of my two-dimensional random variable. Okay, so that's your expression, that's where it comes from. Compare this to his expression here. You can see that here he's writing that f is as the probability, okay, probability that each component is less than or equal to the corresponding value. And he didn't write the integral expression, but we could write the integral expression. This is going to be the integral from x1 to, I'm sorry, that's wrong, from minus infinity. Well, let me do it the way he does. I'll do from minus infinity to x1, and the top integral was going to be minus infinity to xn, and this is going to be the probability density function, and I'll do it like this. This is going to be y1 up to yn, and the integral is from d, because the integral sign's going this way, I have to reverse them, is dyn up to dy1. Okay, so that's your CDF for a vector random variable, and you call that a joint distribution, because you can think of a vector random variable as a set of n random variables.